I'm Ali Bruce. I'm an astronomer at the Royal Observatory, Edinburgh. I normally am doing research involving quasars and active galaxies. I also spend a bit of time working for the UK's public engagement campaign for the fantastic James Webb Space Telescope. I'm not an expert in the moon landings, but I am a nerd. This is the Saturn V Lego rocket. There are many like it, but this one is mine. I would like to take you to the moon and back Apollo style, so hop on board. If you've never seen the Saturn V before, it's basically just a big stack of fuel. You got engines here, fuel, 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 fuel. Engines here, fuel, 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 fuel. Single engine here, more fuel. Inside here is where the Lunar excursion module is, or LEM for short. That's tucked in and all nice and cozy. Then you got an engine here, more fuel, a little bit of oxygen, because in this single piece of Lego right now, there are currently 3 astronauts. That's your Neil, your Buzz, and your Mike, seeing as we're doing Apollo 11. And then just above them, you've got the launch escape system. And now that's designed to pop the cork of the rocket, lift off the command module, just in case this first stage decides to explode. Now, if we're going to go to the moon Apollo style, the first thing you need to do is figure out where the heck the moon is. If you want to measure it out, do it in footsteps. If the Earth is 1 footstep across, then roughly speaking, the moon's about the size of your outstretched hand. Now, to get the distances right, you're going to have to walk 30 footsteps. 30 is your magic number. 1 footstep for the Earth, 30 footsteps, then you can put the moon down. Now, at that same scale, every other astronaut ever, so that includes the International Space Station, all of the Space Shuttle launches, the Hubble Space Telescope, all of the Soyuz launches, the Dragon launches, that's all low Earth orbit, and that's the width of your big toe from your 1 footstep planet Earth. Only 24 human beings ever went all the way to the moon and back again. Now technically, 9 of these things launched humans towards the moon, but because 3 astronauts made the trip twice, only 24 have ever visited the moon and come back again. Now, the first thing we're going to have to do is fire the rocket. This is arguably the most dangerous part of the whole mission because there's a small but finite chance this will explode, and it's made with Lego, so it may also fall apart. You fire this rocket, you point straight up to begin with, but you're not going to be pointing up for too much longer. This bit of the rocket is very violent, very shaky, and only lasts for 2 minutes and 48 seconds. After that, you lose stage number 1. I'm going to need some help for this. Right, good luck. 3, 2, 1. Yes! We're still going. Okay, we're on to stage 2. The first stage then pitches into the ocean, and you carry on firing on your 5 thrusters that are at the bottom of stage 2. You also discard your launch escape system. This is where Lego had to cheat a little bit because they didn't have enough pieces. So we're going to have to put the real command module back in here, and now our astronauts have a window. Why, hey. Now, the magic thing about rockets and getting into orbit, you're not trying to go up fast. The game is to use that kicker to get you up and out of the thickest part of the Earth's atmosphere as fast as possible. Then, this is the sustainer part of your trip. This bit of the rocket is actually kind of rubbish. If you fired this at sea level, it wouldn't even lift itself off the ground. It's so fat with the fuel that it has. But it's not designed to make you go up faster, it's designed to make you move horizontally relative to the ground fast. That's how you get into orbit. So very quickly, the rocket will begin to pitch over like this. And it will last for about 6 minutes, the second stage, and the game is to get moving like this. So getting into orbit is just following with style. If anyone's a fan of Buzz Lightyear, that's all it is. You get moving fast enough in this direction, then the Earth's not going to catch you, it's going to pull you into a circle, and that's you in orbit. So you have to get moving really, really fast. Now, the astronauts will be enjoying this whole ride. This takes about another 6 minutes, and then again, you're ditching stage 2. It falls into the drink, never to be seen again. Then you're firing on the Saturn IV. This is the last big booster that the rocket has. You're still not in orbit yet. You have to fire this engine here for at least another 2.5 minutes, and only then do you finally arrive in parking orbit. Again, we're just in low Earth orbit. Remember your big toe. We haven't really gone anywhere yet, and already we've ditched 95% of the rocket in the ocean, okay? We're in parking orbit. The astronauts don't get to relax. They might be enjoying feeling weightless around about now, but they're only going to be in orbit for about 3 or 4 revolutions around the Earth. And the reason they can't hang around is twofold. first things first, they've got batteries in this thing. If the batteries run out, they won't be able to move it and point it. So that's bad news. But more importantly, the longer they spend in orbit around the Earth, the more the moon is wandering around in its orbit. And they have a sweet spot to hit. If they miss the sweet spot, they're going to be wasting fuel to get to the moon. If they miss that sweet spot by too much, they're not even going to have enough fuel to make it out there and back again. So, at the moment, the moon's around about here. They're in orbit around the Earth, and they're doing this. So here's the Earth. They're in a nice circular orbit. If you want to get to the moon, you're going to have to speed up. And what you do is you fire your engine prograde in the direction that you're already traveling. Now, bear in mind the moon is here, but this isn't going to affect the orbit in this direction at all. If you fire your thruster here and now, what it does is it gives you a little kick. Now, if any of you have ever been to a Scottish ceilidh, I'm sorry about your toes, but you get moments in ceilidhs where you have to fling a person across the room. And if you're going to fling somebody, you've got to give them a little kick to help them make it across the room. It's exactly the same. You add a little bit of speed, and what happens is on the far side of the Earth, you'll be increasing how far away you go. You're kicking yourself higher up, and you'll take a little bit longer to come back to exactly the same spot. If you give yourself a big enough kick, that will take you all the way out to the distance of the moon before you start falling back again. So the magic of getting to the moon is to work out where the moon's going to be in around about 3.5 days' time, fire engine at exactly the right spot to get you there in that 3.5 days' time. So that's your Katherine Johnsons, your calculators, your computers working very hard to try and figure out the best trajectory. So assuming that goes well, you fire this engine for about another 5 minutes or so, I think, and then this thing is essentially a dead stick. But that is you on your translunar injection maneuver. You are now on your way to the moon. Great. Now, you might be feeling a little bit space sick. Some of the astronauts did throw up, not very pretty. But they can't rest yet because now they're attached to this thing, and this thing is no use anymore. It's running out of fuel, and essentially what you have to do is get your lunar module before you get to the moon. So this is where I have to be very delicate. Lego have done an amazing job here. I'm not sponsored by them, by the way. You have to discard this, and you discard this, and there is the lunar module in its payload shroud. It needs to be in that shroud because it's not designed for passing through the atmosphere at all. This is a flimsy little thing. The command module and the service module will boost away a little bit using these tiny little thrusters here, flip around, try not to waste too much fuel while they're doing this, and come back and dock with the LEM. Once you're docked with the LEM, you can remove the LEM from its house. I've left behind an engine, hold on. This is now a dead weight. Now, it turns out that NASA had control over that just a little bit. So if they wanted to, they could put it on a collision course with the moon directly. And they actually did do that because then they have a known mass of object hitting the moon that they can then register on the detectors that the astronauts left behind. So, here's the important bit. You have 3 humans in here right now. There's a little tunnel connecting the 2 spacecraft, and you're now on your way to the moon. 3.5 days. What you do is you go into what's called the barbecue roll. So around about 1 revolution every 20 minutes or so, you've got the sun maybe from this direction, and that's to smooth out the heat load on the spacecraft. You don't want to cook one side too much, so you do that slow spin. And 3.5 days. You've got tasks to do, you've got checks to perform, but bear in mind, imagine you were in a transit van. 3.5 days in a transit van that's hermetically sealed, so you can't roll down the windows, and it's you and 2 of your favourite work colleagues for that amount of time in a transit van. You have 3 couches, you could potentially remove the middle seat if you want, you have a small equipment bay that you could tuck yourself away into, but other than that there's no privacy. All of those bodily functions and smells and private moments are there and coming with you to the moon. Just wanted to give you that nice picture. Now, you're on the way to the moon. The moon is roughly doing this, and you're sailing out towards it while it's happening and slowing down the whole time you're doing this. Now, they're on what's called a free return trajectory. That's a safety maneuver, essentially, because if this engine on the main service module here decides to break, doesn't matter. Free return trajectory means you're coming home for free, and that's because you're moving fast enough in the right direction at the right time so that the moon will arrive here, you do this wonderful figure 8 round behind the moon will fling you back towards the Earth, but you didn't slow down to park around the moon, so you keep going, and you'll make it all the way back to the Earth without having to do a thing. That's why it's called free return, and it means the astronauts have a little safety net just in case this thing decides to break. Assuming you want to stay around the moon and this is working, what you'll do is you have to brake. It's the exact opposite of giving yourself a kick in the prograde direction. You have to thrust against the direction you're traveling this time. So here is the moon. You've been looped around behind the moon. On the far side, where NASA doesn't get to see what's happening, you have to fire your engine to slow down. And when you fire your engine here, what happens is that the high point of your orbit all the way over here will shrink all the way down to give you a nice perfect circle around the moon, assuming you fire this for the right amount of time. Now NASA couldn't see this happening. This was a really nervy moment of all the Apollo missions. You have to fire your engine on the far side of the moon. NASA had 2 times. You came out at the earlier time, they knew your engine hadn't worked and maybe you're going to be coming home. If you come out bang on time, they know you're in the orbit that they had predicted for you. If you don't come out at all, then they're not going to know what happened. Maybe the engine exploded, who knows. Luckily that never happened. We are parked. We've managed to thrust, got a nice circular orbit, and here we are above the moon. Lovely jubbly. But we haven't done the main event yet. So bear in mind this is Apollo 11 at the moment. We have Mike Collins in the command module. We kit out the lunar module here, check out everything's working. As soon as we're happy, Neil and Buzz say goodbye to Mike. Now spare a thought for Mike Collins. Currently my favourite astronaut. Now Mike is arguably the loneliest human being in human history because soon he's going to go around the far side of the moon and he's literally on his own. His 2 mates will be gallivanting on the lunar surface on the near side, and then in that direction, which is far enough away to be covered by your thumb at the distance of the moon, is the rest of humanity. Mike's on his own. Now according to Mike, he actually really loved it. The command module was cozy, the whirring of all the equipment, and to be honest, he had NASA in his ear half the time when he was on the near side, so Mike's fine. We'll put him down for now. Then we got the big show. 13 minutes of scariness. There's a little tiny descent engine on the lunar module here, and this lunar module is lightweight, now really lightweight. There are no seats, the windows are tiny, the astronauts are essentially held to the ground with a bit of Velcro and they're holding onto the joysticks, so they'll be standing up in this thing. But to begin with, the descent engine has to slow down all of that horizontal speed that they built up. So imagine the lunar surface is here, they're coming in this direction, and once NASA gives them a go, they've already lowered their orbit to bring them within about 15 kilometers of the lunar surface, just high enough to avoid all the highest mountains. NASA gives them the go-ahead for the powered descent. The engine switches on. Now this engine is capable of throttling, and the guidance computer inside the LEM is smart enough to adjust the throttle to give them exactly the loss of power, the loss of horizontal speed, and control the vertical descent all the way down. So the computer's doing a really good job here. Now, it takes them a little while to slow down, but you'll note that the only windows that they're able to look out of right now are actually here. They're pointing up the way, and they can't really see anything. They're trusting in that guidance program to do its job. Once they get slower, they start to pitch over, again, to control how fast the moon is able to pull them downwards. And eventually, there's a nice moment where they get to pitch over quite a big distance, and they can finally see where their landing zone is going to be. Now, the computer is telling them a little number. They compare that number with etchings on the window of this thing, and line up the lines. The line of sight will tell them roughly where the computer is saying, you're landing here soon. And this is the point where Neil goes, oh, because he knows he's going to land long. And he sees that he's coming towards a boulder field. House-sized boulders, this is not a good place to park something that's a similar size. So he decides to take manual control and actually stop doing this for a normal descent and actually level off. And by doing that, he keeps that horizontal speed that he's got and does a little sort of hover, if you like, all the way across the surface. And he times that so that he clears the boulder field, clears the crater that's also part of that boulder field, and then actually pulls up at the end to slow down again, and eventually a nice soft landing on the moon. Now, at this point, spare a thought for Margaret Hamilton and her MIT team, because she was the head software designer, if you like, who was programming the guidance computer in here. And this computer was having trouble because it was getting overloaded with data. There was too much information coming to the computer, and essentially it was crashing every 6 seconds. But because Margaret Hamilton and her team had designed a smart computer that would immediately recover and pick up on the most difficult, high-priority tasks, the ones the astronauts really needed, it meant the astronauts could continue. So even though they were getting all these alarms saying the computer was struggling, it was crashing, recovering, give them what they needed, and the astronauts made it. So essentially, Margaret's one of the reasons Neil and Buzz actually made it to the surface. They might have had to abort if the computer had crashed outright. So fair play, Margaret. They make it to the moon. Now, Apollo 11 was the get to the moon as quick as possible, plant a flag, grab some rocks and come home as quickly as possible mission. Okay, it was all about doing it and getting them home safely. They only spent a day on the surface and they only got about 2 hours in their spacesuits, so not much time to have fun on the lunar surface. You're also in a region which is essentially flat, so no big rocks other than the boulders to worry about hitting on the way down. By the time you got to Apollo 17, the astronauts spent 3 full days parked on the surface. They spent about 24 hours total roving about in their spacesuits, and they had the lunar rover to allow them to move even further away. They also landed very dramatic terrain. NASA was taking more risks at this point. But essentially Neil and Buzz get there too, and then they have to leave. Now to leave, you realize that the LEM is actually 2 spacecraft in one, and here LEGO have outdone themselves because you can then separate your 2 spacecraft. This bit gets left behind on the moon, get rid of that. You have a tiny little engine. There's nothing in here except 2 humans, a bit of oxygen, enough fuel to get up to speed, and a lot of moon rocks. So you can see how small this is compared to the rest of the Saturn V. This is a lightweight thing indeed, and the moon's not even pulling on it as much as Earth. So you pop back up into lunar orbit. You're slightly lower than the orbit that Mike's in, and this allows you to move a little bit faster, and you can decide when you want to burn your engine to catch up with Mike and meet him in his orbit. And then at that point you're using your thrusters to redock the spacecraft. Then you transfer all of your rocks down the tunnel, get your rocks. Apparently some poo was left behind on the moon. You've got to save every kilogram on these missions, and then you take everything that you need so that this thing is the thing that's going to bring you home. So then you say goodbye to your nice LEM where you've been cozy for a while, and you discard it. Gets left behind in lunar orbit, and within about a month it will have impacted the surface. Lunar orbits are by their nature not very stable, so you can't hang around for too long unless you've got fuel. This is all that's left. Now to get home, all you have to do is the opposite of what you did before. Wait till you're on the far side of the moon, burn this bad boy here, and come home. Now what you're doing is you're raising your apolloon again, you're giving yourself a kick, and it will become less and less circular, extend all the way out to planet Earth. And then again, it was happening out of view of NASA. So NASA had 2 times, and this time they wanted you to emerge from behind the moon at a slightly earlier time. That way they knew you had the kick that you need to come home. So this is you on your homeward bound trajectory. Again, another 3.5, maybe 4 days, say. Imagine the smells, imagine all the lunar dust getting everywhere, which apparently it did, so Mike's nice clean command module is now tracked up all over the place. As soon as you get towards the Earth, within the last few hours, you're discarding the rest of your spacecraft. So all of those oxygen tanks, your primary power sources in here, all you've got left are the batteries and just enough oxygen to see you through Earth's atmosphere. So we call it entry interface. You're going to hit the atmosphere moving pretty damn fast. You're doing a bat out of hell speed. If you're coming back from the moon, you've been falling a very, very long way. Now this is compared to falling back from the International Space Station, for example. You're going to be doing something like 11 kilometers per second. So lunar re-entries are fast, and that way you need a really, really good heat shield. So the one on the space shuttle, for example, probably wouldn't have been able to cope with coming back from the moon. You're coming in really shallow. This is not a straight down and out kind of thing. You're coming in at only about 6 degrees to the atmosphere, and you're skimming it. You can actually steer the spacecraft as well. The center of mass was slightly off, so they could steer it and maybe get a little bit of lift up and down if they needed it. You come through, you bleed off that speed, and the heat shield itself is disintegrating so the astronauts don't have to. It was a heat shield that was designed to fall apart as it was re-entering. It gets incredibly hot, creates a little cushion of hot gases, and that stops the heat from actually touching the most important bit, your squishy humans, inside the capsule. Eventually you've bled off enough speed, you come back to where the atmosphere is thick enough that you can fire your 3 main parachutes off. Now those parachutes were hand stitched together by a team of professionals, and those parachutes were fantastic. Now you had 3 parachutes, you only needed 2 to survive, and that actually happened on one of the Apollo missions, but 3 was your default. Once you're on those main chutes, you're going to come back down, plop into the water, deploy the flotation devices that this thing had, and you've made it from the Earth to the moon and back again. How was it? Thanks for joining us.